Okay, welcome PCS members and friends to our PCS IBS seminar. Today we have a pleasure of hosting Professor Juan Archilla from University of Sevilla, Spain. And let me briefly introduce our speaker. So Juan obtained his bachelor's degree in University of Sevilla in 1982, then master's in physics in 1984, and a PhD in physics in 1992, all in University of Sevilla, where he also started his academic position as assistant professor in 1982, and then went through the ranks, and in 2020, he became a full professor, tenured at the University of Sevilla. He also was a group head at the group of nonlinear physics in the period from 2017 to 2019. And he's, since 2013, he's a member of European Physical Society. Juan's research interests are localized excitations in nonlinear systems, such as breathers, solitons, kinks, charge transport by lattice excitations, defects in semiconductors, and nonlinear physics in biomolecules. Today, Juan will talk about nonlinear energy and charge transport in silicates, experiments, and semiclassical models. Let us welcome Juan.
Well, first I would like to thank you, IBS and PCS, Sergei Fla, for inviting me to this visit, and also Dylan for introducing me. And here in these first slides are all the main authors of the work I will be presenting, but this is the continuation of work with different people, and which are listed well below that. Some people working in experiments, some people working in pterochines, and Masayuki Sato, who introduced me to spectral theory, and certainly with some person from a researcher from Cameroon, Alain Togio-Motchenko, the draw waves. And this is more or less the outline of the talk. I do an introduction to breathers because maybe it is not completely well known for everybody, although it's quite the standard nowadays in nonlinear science, but I think there are people with very different backgrounds. So I think it will be good to have that introduction. And there will be some detours, something about the system of interest, which is mica muscovite and related mica materials, some experiments which motivate our research, some modeling. Then, because of the need to find a exact solution, we do this spectral theory of breathers or kinks in the moving frame. And then we'll actually go to type in the semiclassical models and then spectral properties. So the introduction to breathers, I will switch because it's very easier seen, at least initially, with some videos. Let's see if I can get them. Yes. So this is one breather in one dimension, which is vibrating with a single frequency, although it can be more complicated things. This represents atoms or particles. And as we can see, there is this is a very sad breather. We cannot see anything propagating on the lattice, just the vibration of this breather. And with some manipulation, we can make this breather to move. It looks much more complicated. It's not easy to get exact breathers. They tend to radiate, but we have obtained actually exact breathers in some systems. And in this case, due to this non-exact propagation, we can see that the lattice is being affected, and we can see everything propagating in the lattice and some perturbation.
Yes.
Yes?
What is basic?
Pardon?
Is this? What is this? Amplitude, mechanical amplitude?
This is the displacement from the equilibrium position
Or what?
The atoms or particles.
It's a chain
Mechanical
of one.
Pardon?
Mechanical
Yes,
displacement.
yes.
Mechanical okay.
Yes,
This is a displacement and this is displacement.
exactly. This could be
Dimensional system.
it could be a displacement from actually in the same direction or transversal. Yes, different possibilities. I just want to.
What is the difference from the optical phenomenon?
Pardon?
Optical phenomenon.
It can be related with the optical phonon, but also with acoustic phonons.
Mixture of,
Pardon?
it's a mixture of optical
No,
and phenomenon.
typically one or the other. One or the other. And here it is with this is a radar obtained with molecular dynamics with lamps in 3 dimensions, but we are just seeing these 8 atoms of germanium. And then what we see is we have this vibration of these 2 atoms of germanium, which affect a little bit to the neighbors. We see another picture, and this we call them breathers because it reminds at least of if we do our reproduction it at the right speed, it seems like it is something breathing at this figure.
May I ask a question? Because not on a previous video, what we see actually relates to non-linearity system.
Yes.
But here for this atoms, we can we obtain this picture using only linear equations?
We see what?
Linear equations
No.
without non-linearity.
No, you use for germanium distribution of terms of potentials, and they are nonlinear. They are linear at or quasi-linear at low amplitude, but they are intrinsically nonlinear. So this is one view, and for the same kind of vibration, we have now a slice of germanium. These are these 2 same atoms. The frequency propulsion have changed a little bit, and we can see that actually it tends to propagate a little bit around, but it has a very long life. And this is a stationary breather. And here we are, this is also with doing molecular dynamics in 3 dimensions, but we are representing just one row of in iron. And we can see here the displacement, transversal displacement of some vibration, which is propagating through in this closed packet line in iron with molecular dynamics. Okay, so.
Sorry,
Yes.
what do you use to create these solutions in the system?
What? We just produce what
How you create these solutions?
It exists. Solution exists.
Yeah, but in nature, but like excited, what I should say.
These are not obtained by me. This is by some colleagues, actually, Dubinko from Ukraine. Well, there is some answer that you have look for some mode, as somebody you said maybe from the pi mode, but then you put some amplitude for some of them and not for the other, and with some art, then you can get this kind of solutions, and they have I will not use that in molecular dynamics, it's just an example, but they have done it many different materials, like vanadium, iron, many others.
It is possible to interpret as this kind of thing is phonon packet, or similar to the wave packet is a phonon is a packet.
The thing is, wave packet, it is usually it means a superposition of linear waves, and that produce that localization. But because of they are linear, then each one have a different speed, and then the wave packet usually does not live long because these components separate. And then, because this is a nonlinear entity, then its life is much longer. And in some cases, when we can get an exact solution, it can live forever. So Soliton, we shoot when there is no vibration. We have just the shape moving like this. Yes, although sometimes definition is very clear because it also depends on which variable are you representing. For example, some people will maybe represent the amplitude for this movement, and then it will look like a soliton. Yes. So, yes. So this is basically to see what we are talking about, and then we'll go here a little more information about this, I think, very nice example of breathers in germanium. And if we do the spectrum of this distance, of this distance between these two atoms, we get this very neat, of course, a zero temperature. This is this very neat spectrum. When we have one frequency and multiples of it, we can see that the second harmonic and the third harmonic have quite high amplitude with respect to that. That indicates that the vibration we have is highly nonlinear. And if we look at it with respect to the spectrum, these lines are the theoretical spectrum of germanium, and these experimental, these dots, the very frequency is up here. So it's quite high above and the frequencies or energies of germanium, of theoretical and experimental. That's why that frequency does not radiate, and it can have a very long life.
This is linear spectrum of linear.
Yes, exactly. Exactly. In this case, we can see that it is very high above this the highest frequency, and this is appearing in the spectrum I showed before with this very important second and third harmonics. Okay. So our interest is this Michael Moscovite and related materials for reasons we will explain shortly. But let's first see what is the structure of this material. And we have in this tetraedra or octaedra, we have oxygens at the vertex, and in the middle, they have in the tetraedra, there is aluminum or silicon. But what we are interested in especially, it is in these yellow balls, we represent potassium ions. Potassium ions. These potassium ions are subjected to their own interaction between them and the interaction of every one of them, and the interaction with the layer, the oxygens, or also silicon, whatever it is up there. But first, the nearest neighbor are oxygens, and they have this hexagonal structure, as we can see here. So we will do some relatively simple but also relatively complicated models to represent the movement in one of these rows, also something also in this two-dimensional. The important thing is these potassiums, some of them are, the atomic mass of potassium is 39, but the most common isotope is potassium 40, which is radioactive. It suffers beta decay. It's actually the most important source of radioactivity for humans, especially when we eat bananas or other things. But we'll have some role in that. Okay. So, and this is interesting for us because we are going to see evidence of quasi one-dimensional propagation of nonlinear excitation. There is fossil evidence, fossil meaning nuclear tracks, but well, I won't talk about that, but we will talk about other evidence which we will see in a minute. But there are also the things of interest, which yes, I think it's worth mentioning. One, it is that experimental evidence of the role of breathers in those layers in reconstructive transformation. They happen, this reconstructive transformation, at much lower temperature than it would be without breathers. It's for other authors completely different. It is proposed as the origin of life, because this confined environment with potassium is particularly the zinc. I don't know about that. It is related with the original life. And some very interesting Korean researchers work in monolayers, bilayers, or 3 or 5 layers, and then they can control the properties. Muscovite is a very good insulator, probably the best natural insulator in the world. But when it is only 1 layer or 2 layers, it can be a semiconductor, can be a semi-metal, can have different properties, and that can be modulated. Okay. So, and this is done by co-workers, Mike Russell and others. And this is the experimental demonstration of quasi-dimensional propagation of solitary waves. The acronym for this quasi-one-dimensional, it is quadrons. And this is experimental setup, means we have alpha particles source here, and it is at some angle to prevent that something is propagating. Actually, it's not the direction we are measuring what happens. Here is a monocrystal of muscovite, where the sheets are horizontal in this picture. And here in this setup, it is done to if an atom is expelled, it is ionized and detected and counted. So what? And then we can know, because I didn't do it, we can rotate this sample. So it can be shown that we have a significant number of atoms exposed when the position is such that we have a close packed line of potassium ions in that direction. So it means that some energy is propagating, produced initially by alpha particles, but it is propagating the lattice, and then with enough energy to provide the expulsion of an atom at the other end. And that was in 2007. I started to collaborate with Russell some time later. And for different reasons, we deduced that, at least in many cases, this quasi-dimensional excitation transport electric charge. That's a very important step, because if we have charge being transported, we have something to measure, which is electric current. And this is Mike. Mike was working in particle physics most of his life, but at the beginning, when he retired, he dedicated to nonlinear lattice excitations as honorary professor of many universities, including mine in Sevilla. And as you can see, it's quite old. So the experiments, when we call it hyperconductivity, consists as a variant of what you can see. We have a source of alpha particles, we have a monocrystal of muscovite, and we have an instrument to measure the electric current. An important thing is there is no electric field. There is no electric field. And so it happens that we detect a current when we switch the alpha particles. We detect the currents. So I'll show you small details later in a minute. And we detect a current which is flowing through in this muscovite. And this is given to these different papers. And interesting one thinking about what it is could be the consequences of the problems in tokamak reactors. Because in this environment, there is a lot of alpha particles that then, in principle, as we can see here, we can produce a maybe transport charge, and probably some problems in how to be taken into account, at least. So this is a typical hyperconductivity experiment. And what actually I think it was done in Sevilla, but then has been done in UK. Yeah.
I have a general question. So you're talking about nonlinear excitations in the system. Does this mean that in order to observe this excitation, we need to create some highly non-equilibrium situation in the solid?
We need to have some relatively strong perturbation or deformation or velocity of the lattice.
And then, does it mean that we need to create very localized excitation?
Yes, but experimentally we don't have the means to produce that. The thing is, alpha particle has a huge energy, it's like 5 MeV, and this kind of excitations, if we are things, maybe 20 MeV, 20 electron volts. For breathers, maybe 1 or 0.1 eV. So this alpha particle will produce so many things, and some of them will evolve in what we call quarks.
Point-like excitation.
Yes. Probably very few of them, but there are so many things will produce at some time.
Is alpha particle
Yes.
real?
Yes.
Which has mass, position,
Yes.
maybe.
And charge.
So this is like complicated molecules.
Replicated?
It is molecules.
Well, it's an ion, no electrons.
Huh?
It is an ion. Alpha particle, it has no electrons. It's just two protons, two neutrons.
Okay. So, but this is a part.
Yes. Yes. But the reason to use alpha particles, it is quite easy to use, because it will be much more convenient to use some other source which is much lower energy, much more under control. Like, for example, particles in a plasma, but then there are other problems of how to use the plasmas and how it influences. We have not succeeded in that. So it is not the best thing to produce this kind of entities, but it is the easiest and the cheapest. As a curiosity, the source for these alpha particles was just taken from 3 smoke detectors, which at that time in the UK were still legal to buy. And then from the 3 smoke detectors, we get americium, and it's the activity it has is enough to produce and destroy the experiments. Okay, so what we see here, it is that we can see here there are very different things happening, at least 2 different things happening. And the difference it is that when we can see these things here, it is when the alpha source is open. Alpha is a gate that stops the alpha particles, and then when it is open, we can see this current going through the material. And then we say that it stops, and then push it on, it starts again, but with decaying intensity. The current becomes smaller and smaller. And what happens here at the end, it goes back to a limit value, and this limit value, it happens to be exactly the current taken by the alpha particles. They have electric charge, so this current is what we will measure here at the end of the limit. So what has happened before and why the case? Well, the explanation it is that we have a small but significant reservoir of electric charge in muscovite, because the most important source of branch of decay, it is beta minus. So then an electron is expelled, and then you have an extra charge in the material, and then maybe eventually they will more or less. That's a very good insulator. It will move, but at some given moment you have still a population of positive charge due to beta minus decay. So the reservoir, it is the charge which is moving, but this charge being depleted, then eventually there is no more, and then it means that you have only the charge transported by the alpha.
So how do you interpret these jeeps and heights?
Here it is, we stop the flux of alpha particles.
Sorry?
We stop here the flux of alpha particles. And we switch it again, and so on.
So am I correct that you interpret this conductivity which you generate, this the propagation, that these solitons are carrying charge, and this is charge carried?
Yes. Yes, that's the interpretation.
And what would be the proof of this?
What will be the proof of this? Well, I don't know. Well, what will be the explanation if not?
One of possible.
But it could be an explanation, but it seems a reasonable explanation. explanation. And but there is no proof. The proof is that we have this effect, and we think that the likely reason for that is this one. Yes, an interesting analogy it is with respect to in the sea, we have waves which are like phonons. Then we have a tsunami or a big wave, like maybe you have heard about bowls in some rivers. That is a solitary wave, maybe, or sometimes one or two. And then, omnicombustion will be like a boat. We need some source of energy, like wind or motor, rowing. But in this case, the electron will be using the energy and momentum given by this wave. A surfer, a surfer riding the glasses. That's an image. An image that explains a little bit what it is. But yeah.
I have a question. At which temperature was the measurement performed? Room temperature. Okay. Because this is like in femtoamperes, so isn't it like? I mean, because like for instance, when you measure nanovolts, then it's kind of crucial to have like very low temperature due to like thermal oscillations and this sort of thing. So doesn't it like bother the measurement here?
It is, and it is a very interesting thing that it happens at room temperature. Yes.
At low temperature, we still may have strong heat.
Well, current is very small. Current is very small. And the time of is it's actually not that small.
Yeah, ask you one stupid question. For the current, yes, system. What about the mass transfer? What is there some mass flow in the system?
Sorry,
Mass. How to detect mass?
That's
a solid state.
That's a very interesting question because two candidates for transporting charge could be, on the one hand, will be ins, which is basically a moving interstitial, or breathers, which is just a vibration. And because it is an ionic crystal, a moving interstitial will transport also charge and mass. But we have to detect that mass. I don't know. But of course, the detection of mass will be a way to differentiate between these things. Okay, here you have two different materials. Which it is this is a artificial monocrystal. It's fluorofluoropite, a similar material, but can be produced artificially. And then this is just also the switching on and switching off of the current. And we have this slow decay. It's a slow decay. The slow decay means for us, especially if we compare with this, which is a natural crystal, not so good. We have this abrupt decrease of the current when the alpha source is switching off. And so interpretation it is that when we switch off the source of energy, still there is some time where things are propagating, maybe rebounding, maybe changing, but still there is still some propagation that store current in the, and with a component in the direction of the alpha particles, of course, and it is still propagating. Okay. So we try to produce a model for this relatively simple as possible, but at least with the necessary things to try to see if we can find this kind of propagating entities or quadrants, as we call them. And the model it is just for one row, one dimensional. Something about this I will show later, but essentially it's one dimensional, and it has just Coulomb interaction. It is of course made scale, so to make it simpler. This represents it's called the ZBL potential, represent the repulsion between nuclei, but screened by the electron cloud. And this represents the contribution of the atoms, interaction of atoms above and below, and also the adjacent rows. And being quite simple, still it gives things like, I think it was here, maybe in the following line. Anyway, reproduce, for example, the infrared spectrum of longitudinal vibrations, the interstitial energy, and things like that. This is the subtrace, I can see it written. This is the potential, which is, it is at the end of the day, because it is periodic, it is a sum of cosines, and it is enough to a big precision. It was the terms. It has the shapes with shallow here, and so on.
You assume electron is homogeneously spread.
Pardon? Here there is no electron. I just know that.
You do not calculate the current.
Pardon?
Your
In this model, still there is just ions. There is no extra electron in the
current is based on the ion,
Ionic.
but the electron is not.
not yet. Not yet. Not yet. Because the important thing that experiment, those experiments also shows that there will be many neutral quadrants and many neutral localized excitations that we will move to the system. Why? Because there is no reason that we have very many at the beginning where is this reservoir, and then they are not produced because the reservoir is exhausted. So we have reason to think that there will be many neutral nonlinear excitations, traveling quadrants, as we call them, quasi-one-dimensional excitations. But we can only, or at least in this type of technique, we can only detect them at current when they travel. Okay, so this
is dielectric.
Pardon?
Dielectric.
Insulator, yes. Dielectric. Very good insulator. Very good. I think it is the best insulator, natural insulator. It was used for insulating everything before plastics. And they will also use some model which is more simple. That's proposed for this kind of system by Jars, Elvik, and before collaborated with them into this. And this is not so good in representing physical quantities and physical interaction, but it's also very reasonable, just interaction, Lennard-Jones, and Frenkel-Konturova for the on-site potential. And we also have the one-dimensional version of it. And the nice thing of this system, it is a very good testing system because it is very easy to produce localized excitations that travel very well in 2D or in 1D. And that's why we see that because it is, the other system is quite difficult to get anything.
I have a question. Do you consider there are some missing of potassium? Maybe frequency also can move through. Alpha particle is a lot of momentum and some potassium is outside.
Alpha particles will produce what is called a thermal spike because it has a lot of energy. But from that, many things will move around, and we suppose that some of them will be some excitation that travel long. But initially, it is not a one-to-one thing because the energy of the particle is huge. So many, a million times the energy that you have for these kind of things.
Frequency can create enough.
Pardon? So it is a little bit like in this analogy with tsunamis, you have an earthquake, produce a lot of energy there and then also produce a tsunami. But then as your earthquake is much larger. But in some conditions, it will produce a solitary wave like a tsunami. So this alpha particle impact is like a earthquake in the system.
So here you have like a large number of 1D chains. It's not just one 1D chain, but it's a huge number. And
yes.
So that the ones that maybe where you kick potassium out, it's different effects, but you will still have.
In that sense, what is a very interesting source of this kind of excitation is the own decay of potassium 40, because that energy is much lower. It is depends It actually is a continuous spectrum of energies from 0 to about 47 or 50 V. And so there is a, because it's a three-body decay with some neutrinos who take energy, so it will produce many energies, but are in the range of the spectral energy of this. And but of course, we cannot control when 2040 decays or not. Okay. So then with these models, and generally speaking, we thought, well, we have to look for exact solution of either breathers or kinks because they will live much longer. And this is in one dimension or 2 dimensions, is related to these articles. And so basically the idea is to look at the spectrum of these solitary waves. And here is in 1D. We have here a frequency. This is wave number frequency, a frequency, and we have some extension in K, in wave number or wave momentum, which means that the extension means that the wave is very localized, has a single frequency. We have here also something here with 0 frequency, which means it's just a deformation, no vibration, just a stationary solitone or kink. And this is the dispersion relation. In this case, in this example here in this spectrum, this is related with the pipe mode, which means that particles will be more or less in antiphase. And as you commented before. But we also can have breathers here down. They are clearly not in the dispersion line, and can be here or can be also here below, depending on the system.
So just for education, for linear, I understand the spectrum for linear excitation. For non-linear, we used to think that frequencies start to depend on amplitude.
Yes.
And so on. There is no amplitude here presented. In what respect is spectrum?
It is not, but we can see here that we are not in the linear range. So it means that the farther away it is in this line from the linear, then the amplitude will be larger. How much? It depends on the system. And
so there must be some amplitude present.
This is what we call a hard system or hard breather, because when we increase the amplitude, the frequency increases. And here, from this mode here, we will have the line like this, which means that when the amplitude increases, the frequency decreases will be a short breather.
Curves are for different amplitude.
This is for very low amplitude phonons, and this is for some specific amplitude. But with a large amplitude, we'll get a similar line a bit farther away. And with lower, we'll get lower here. Yes. And then the thing is that this breather is a non-propagative breather. It's only a mixture of breather and solitone. So you have these 2 terms here. And then what am I going to say? So here, we have something similar to a packet, but because this derivative is 0 of omega with respect to Q, it means it has no propagation. Also, it comes from this mode Q is equal to pi, which not propagate, it's just some alternating vibration. It means that when you have a moving breather, we'll have something similar, but this line will be tilted, and this is what we can see here. This is a fast Fourier spectrum of a simulation in the model A. And we have here like something like a line. Of course, it's a very approximate. It's not a very good breather. It continues here because just of the periodicity of Q in the reciprocal space. We can see here, what is here is some phonons because are also here in the dispersion line. And very interesting also we have here, if we prolong this line here, we find here something which it is almost localized. We call that a wing. It means there will be some extended quasi-linear because we are basically here in the linear dispersion curve. We have a quasi-linear extended mode vibrating in the system at the same time. So what else is here is basically this. Okay. So then we wish to define an exact solitary wave, and it will be given by a function in one dimension. We'll go then in more dimensions. Will depend on two components, one this term and this other term here. Will be partially localized in this variable, and will be 2π periodic in this other variable. So in this W hat here will be the moving frame frequency. The frequency is somebody is moving with the breather, because in this case this will be 0, and then we have only that frequency. If in this we don't have this term, only that, we'll have just a shape. It's a shape which is moving, and then we'll have a soliton or a cube.
What is the definition of partially localized function?
Partially localized. I think the word partially here, it is because if it is a king, then will be localized on one side, but not on the other. That's why it is introduced. So, I have going too fast. Then we define as a solitary wave some solution of this form, which has the property that we define this fundamental time and step. The meaning is that after this fundamental time, the profile of the wave is reproduced, but displays as number of sides we call the step S. So this means that the velocity of the breather will be the step divided fundamental time. This will be the fundamental frequency. This is also important also because it's the frequency related to the velocity. That means the frequency at which an observer moving the breather meets each particle, different particles. And then to have a solitary wave with a simple analysis, it means that we have that this frequency in the moving frame has to be an integral multiple of the fundamental frequency, an integral multiple of the fundamental frequency. That's the condition for that. I think I have gone too far. No, I think it's okay. The nice thing of having a solitary wave described in this form is that we can reduce the basis in which it is represented, the basis of harmonic functions, because we can construct harmonic functions and put it exactly in that form. And if in this term here, if we comparing these two solutions, it means that the laboratory frequency we have here will have this form: Q velocity plus M fundamental frequency. In other words, we will have that the solutions, the harmonic ways that we need for solutions are have frequencies which are straight lines with the slopes of the velocity of the breather and with a frequency in the moving frame which is integral multiple of the fundamental time. Graphically, we get this picture, which can be complicated, but it's also very simple. We have a dispersion line here. We have here the breather band, this intensity is here. And we have the possible resonant lines where we may have components, but there is nothing here. Only here we can have that this resonant phonon is cutting the dispersion line, so we may have here a wing, not necessarily, but we have the risk of having there a wing, because we have a phonon which is traveling with the same step and with the same frequency of the wave frame. So we have here a soliton, because here for Q equals 0, the frequency moving frame and the laboratory are the same. From here, we can see also from this difference, we can see what is the velocity frequency. And we can obtain the parameters of this solitary wave just by observing this spectrum and having some calculation. This is done for step s equal 1, for step s equal 2. Instead of here just this line and this line, we have another line in the middle, or more, have more.
Sorry, short question there. This S, you define that this parameter in the previous slide. I think you can easily change this in your calculation, but in the experiment, can you also control the?
No, not all.
No.
We can observe and to see the exact wave is more close to one thing or the other. We cannot control it at all.
I see.
Okay. This is we change to the moving brain frequency with these answers. And then the picture becomes much more clear. The dispersion curve is changed. And then this is the moving frequency with respect to fundamental frequency. So we have that there are this band, it is all of in the moving frame, it's just a single frequency. Also, we have here a single frequency for the wind. So in this picture, on the presentation, it becomes very simple what we have. We may have only for integer numbers here, we may have frequencies, and here we have, because it's very close to this top here, because this will be stationary in the moving frame, we will have this stationary band here, and also this one frequency. And this is an example a bit complicated in terms of numbers, so step and that, but I will explain that later. And then the generic solution that we find, and in the system I know that it is actually kings and breathers with wings, we call pterokings or pterobreathers. And here it is one is for model, the physical model. We cannot see very well, but this is a standard wave that goes with the frequency we have. But this is a generic solution. But if we change the frequency, this is amplitude of that vibration, and change the frequency, and this is logarithmic, then eventually for some combination, we can find actually breathers with no exact solutions that are traveling in the, it have such a quite complicated shape. This is the amplitude of the wing with respect to the, and actually we call this the tail because there is no wing. There is no wing in this kind of. So for some specific frequencies or for things for specific velocities, there are exact kings and exact breathers. This is interesting because then we have something which can, in principle, travel very long. Just a bit a small detour for rock waves, like in this system, we have here just springs and pendulum. Then appear rock waves that appear suddenly, like this one piece here, appear and disappear, but still we can do the spectrum of this small piece, and we can see that it corresponds quite well to these spectral properties. Here, this frequency is due because this is then in this case it's shaking, the whole lattice is shaking, and then we have this frequency. Okay, so in 2 dimensions we can also define similar things, and I will go further on this. Then what we finally get here in 2 dimensions, this is an example, but going to the spectrum, this is the spectrum dimension, very similar to what we have seen. An important thing is what I've seen. Then we have, instead of a breather line, we have a breather plane like this. And so we have frequency of the breather instead of inside this. We have also a wing plane and a soliton plane. Here, when it is in dark, is when we have actually frequencies measured in that wave we have seen just before. So you have in these planes. And in 3D, we cannot represent it, but it will be similar thing, hyperplanes. And interestingly, in 3D, then this localized wave will be not so much localized, will be instead of this something like this, something like this, different scales corresponding to many different possible breaths in many directions. And then, interestingly enough, for example, for this spectrum in neutron spectrum of this material, I don't know, lithium of selenium, I don't know exactly the name in English. So there is this acoustic band, this optical band, and this band here is more or less resembles what I have just drawn there, and there is a possibility, so can be possibly identified breathers in this spectrum. So that all without charge, let us charge transport. So we add to that model an operator for a hole, because
What is the meaning of this whole thing?
yes, wait a minute. Yes, this is a hole because in this model, what we expect more, it is 99.9 or something like that. It's beta minus decay, so the probability is have holes and not electrons. So let's we talk about hole. So in this will be in the energy when we have an hole in some specific site, and this means the protected this opening or transfer integrals related to the probability of transition from one side to the other. And these terms will have this shape. And because of the overlapping of the wave functions, which is also exponential, have a principal shape like this, and also have calculated this. And the thing it is for our system, and this means that for near the equilibrium position, this will be basically zero, but very, very small. But when the atoms approach, the probability of transmission will increase a lot, and then we'll have the possibility of charge transfer.
So here you have both electrons and displacement.
Yes. So the expected value for the hole will have this term. This is we have this basis. The electron is located in, or the hole is located in one side, and then there will be the probability amplitude of the hole being in that side, and we have this. So we done just for the electron, because also I know have not written because it's a bit long, but we have also this. Let's go, I'll go to that. So for the site energy, we can calculate this site energy due to interaction with the interaction with the atoms above and below, and lenses above and below, and we have also interaction with the other potassium ions in the lattice in the same row, and well, it has some changes. Will not enter in the details of here. And for model B, we also use it. It is very simple, as a constant one.
Is it possible within this model to get electron localized at your solitons and moving together, like carried by solitons?
We have succeeded in this simple model, but not in the other. Or I mean, we have succeeded to a point. Means that it travels, but it doesn't travel so long. Yes. So here we can see an example of what happens when the atoms become closer. This is the position of the two ions, and here they become closer, and then the red line with respect to one, it is the probability amplitude. So we have here that it starts to oscillate with some interchange here, and after the interaction, we can see that we have had an increase in probability here and decrease here. So there has been some charge transport from one ion to the other. The way it happens. Dynamical equations, the Schrödinger equation for the hole, and Hamilton equations for the lattice, taking into account the lattice and the hole, and our equations that I don't want to details. The Hamiltonian equations becomes quite complicated, but it's still manageable. We can write real equations, and we can go to real equations. And this is very interesting because they change and makes it possible that the whole system is completely Hamiltonian. So I'm talking too much. Just a second. There are series problems for integrating, for charge conservation that we solve using splitting methods, but also I will skip about this. So, with these chains, these ansatz, is quite important detail for finding exact solutions, because these chains means we transfer the equation in this other one. We did not equal to mu to this mu, because by tau is the Planck constant in our system. It's important because this, if we want to obtain periodic solutions, we have to play with this value of E naught, because as this is a change in frequency, which has no physical consequences, but for us to find an exact solution, periodic solution, we need, we'll get it for some specific value of E naught.
You know, usually in metal, for example, there is a fundamental parameter which ratio between electronic mass and ionic mass. Yeah. So you expect here this adiabatic separation of electronic degree of freedom.
Yes.
Yes. Then you should get polaron or something like
exactly. Exactly. Well, so let's see what we get. Polaron is in a linear system, I'm right. But it's very similar. And polaron is a deformation traveling with the charge, and here it's a vibration traveling with the charge. But very much similar. What we obtain is in the semiclassical model. Well, we produce in model V, the easy one, we produce in stationary breathers. This is, we have here also these negative power frequencies, which usually we don't picture because it's symmetric, but we need it for Cn because it's a complex number. So you have this more or less complicated thing, but actually quite easy here. But we see many lines. Then with some seeing what be the step, what will be the fundamental frequency, looking at these pictures, then we are able to obtain exact solutions, which are very, very simple and very neat. Just a breather soliton for the lattice. For the probability, we have also soliton and there's vibration. And here for Cn, this is interesting. We have also we can just move arbitrarily. That's the role of E naught. You can just move arbitrarily. So you can see here that this difference here, it is the same as this, which means that is driven by the lattice and the vibration of the lattice. And this difference was also this one here, but I suppose we can explain that I will not go into that. So this is the profile for the charge probability, which is basically a stationary deformation, very simple one. And we do the same thing for moving breathers. We have this like quite complicated breather. It will be a wave packet because it's very close to the linear solution. And we also can manipulating in order we can obtain from here is a solution which look so simple. Yes, we have a soliton, a breather like we saw before. For the probability is just a soliton traveling with the same velocity, and for Cn we have these two components. So if we move this up here, which correspond more or less to what correspond exactly what we have there, meaning that it is produced this vibration by the lattice, by the lattice. And this is the profile. For model A, we have obtained traveling thing, but not so good. Not so good. Let's just comment one thing. We obtain a different kind of localization, which is a chaotic breather. It means this is here UN plus N. The color here means probability of the charge being there. And here are one of the coordinates in time, but a clear picture maybe is this one here. This is for the lattice variables, position and momentum. Exchanging, this is the main one neighbor, the other neighbor, exchanging continuously, but keeping the amplitude. And here it is AN and BN for the whole, the main one, and one neighbor and the other neighbor. And it's changing continuously, but always passing through one, meaning that the charge is conserved. Yeah. Some question was?
I miss what is P and what is U?
UN is the displacement with respect to the equilibrium position. PN in this is a kind of units is simply the velocity of the momentum. Yes, this is the phase space.
Who gets localized in your problem?
In this case, everything gets localized. both the
So
charge
electrons or
and the vibrations. And the vibrations.
and the solitons.
Yes, but we have not a quick constant frequency. It's some chaotic element, but completely localized at the end. It's moving, changing continuously, but not in such a period.
What is A?
A and B, sorry, A and B are the real imaginary components of the whole amplitude. So you can see that one of them here, for example, if we link any of them Bn, here An is 0, we have here Bn. And then we will go, we'll come back, eventually we'll come back to 1. After some time, we'll come back to 1, meaning that the charge is always still there. Some of these trajectories, maybe we'll have that Bn is not 1, but after some time we'll come back again to the 1. So the A and B interchange, but at the end of the charge is pretty localized. And I don't talk about thermalization, I skip this. It's interesting just thermalizing the lattice, we get something traveling. And we can relate it with the system, but I think I talked enough. So I will skip this. Anyway, we can relate it with the spectral relation of Cn, but skip. So this is like a long detour from some experimental experiments, trying to find a right model to describe it, trying to find exact solution and the properties and energies. And we have had up to now a mixed success, but not actually we have not achieved our goal with the physical model of the traveling solutions. And we are working that. Thank you very much for your attention.
Thank you, Juan, for this nice presentation. We have time for further questions.
Just a general question. We know that it's very difficult to generate solid or to prepare it experimentally. Does your approach give more insight what we can do experimentally to detect this?
Well, the thing is, at least the idea is, well, exact solutions in principle, we can think that they are the ones that will have longer life in the system, or a solution close to them, because maybe experimentally we are not going to get exactly them. And they will have some characteristics, some frequencies, some step in the language you have just seen, and very important too, they will have some energy and which can be predicted. So in this way, we can predict, for example, which energies, and also which, that is more difficult to manipulate, but which energies we will expect for those traveling solutions.
Once they're created.
Yes. And what will be their effect? For example, in the first experiment I commented, the one of expulsion of an atom, then we know more or less what is the energy necessary to expel an atom from the surface, which is 7, 8, something like that, from most exact number. So then, for that experiment, we need something traveling there which have that energy. Then we can see, for example, that one breather, this, as long as this model is more or less accurate, one breather will have not enough energy for that. For that, we will need a king.
Very short.
Yes. Which the energy is about, I haven't talked much about kings.
So you're saying that you may estimate numbers.
Exactly.
And once you have an experiment evidence of these numbers, would be good evidence.
Exactly.
Any other questions from the audience? Seems not. So then let us thank Juan again.